Hello everyone, welcome back to another video. So today we'll discuss editorial for weekly contest 432. I was able to solve first three problems, so we'll only discuss solutions for first three problems. And my rank is pretty bad, 975. Mostly it is because of these four penalties. Made one penalty on second, and there are four penalties on third. I solved pretty fast, I would say 58 minutes. Is good enough to get a 500 rank, but because of these four penalties, my rank is 97 975. So let's just start with first problem. So we are given a grid of sides m into n, and we need to traverse the grid in zigzag pattern, and we also need to skip an alternate cell. So what zigzag pattern is? You start from top left cell and move right up till the row is until the end of row, and then drop down and move to next row. Now when you move to next row, traverse left until the beginning of the row is reached, and we have to continue this alternating. So in first row we have to move right, second row we have to move left, third row we have to move right again. So in that way. And let me just so this is the grid, let's say. So alternating means going this, then dropping down, then going left, then again dropping down, then going right. In this way, we have to iterate the grid, but there is additional uh, condition that we need to skip alternate cells. So first example is of 2 by 2 grid, and the elements are 1, 2, 3, 4, and the output is 1, 4. Now here 2 is the if we don't skip any cell, the output would be 1 2 4 3, but when we skip one alternating cell, so it becomes 1 4. Similarly to for 3 by 2 grid, there is the answer is this 2 1 2 for some configuration like this grid, and for this it is 1 3 5 7 9. So as this is a first problem, the constraints are very low, and expected answer is brute force basically. Now how can we iterate this? One way of doing it is based on row number. So one way of doing it is based on row number. So this is first row, second row, third row, and fourth row. Now let's just mark them in zero based indexing. So all the even rows, so 0, 2, then 4, will move in right direction, and all the odd number rows will move in left direction. In this way, we can do it. Now, for skipping condition, what we can do is we can iterate the grid normally first, and then after that, we can remove all the alternate cells. So that's the brute force logic which I used here. Let me just show you the code. So first of all, I declared three variables. I, J are the coordinates in the grid. ch is nothing but a direction which it's in which we have to move, and then I have declared a vector to store all the to store the results. Now I'm iterating over all the rows, and then I'm iterating over all the columns. So j basically represents column number, I represents row number. Now uh, for first row, our ch is 1, which represents a direction. So this condition is for checking if j goes out of the window of column numbers, that is if it is not in between 0 to m and j plus ch. So if ch is 1, j will be incremented, that means going to right direction. Once all the elements of that row is processed, we just increment I, move to next row. But before moving to next row, we just change the direction. That is, if ch equal to 1, that means the current row was moving towards right side. Now when we were moving towards right side, the last column which we processed was m minus 1. So we set j equal to m minus 1 and set ch equal to minus 1. Now next time the direction would be towards left. So whenever ch would be added into j, it would be minus 1. So basically decrement will be done here. And if ch is 0, that means we were moving towards left. So starting position of j should be 0 and direction should be reversed. Now answer, we store uh, all the integers on that zigzag path. Now we have to skip the alternating cells. So for skipping it, I have declared another variable, and here I am just iterating over answer vector, but the index is skipping a alternating element. So I plus equal to 2. So 0, then 2, then 4. So 1 and 3 elements at index 1 and 3 are skipped, and then I'm just returning that result vector. This was the first question, pretty simple. Next move, let's move to second one. Second one, again, we are given a grid of size m into n, and a robot starts from top left corner, that is 0 comma 0, and robot needs to reach m minus 1 n minus 1. Now the robot can move either right or either down at any point of time, any point in time. So pretty standard uh, DP related question, I would say. This is pretty standard. And additionally, the grid contains a value which is coins of ij, and if coins of ij is greater than equal to 0, the robot gains that many coins. But if they are less than 0, there is a robber which encounters the robot encounters a robber, and robber steals absolute value of coins of I comma j. Basically, we lose coins of I comma j ij. We basically lose some coins when we encounter, when there is the coins of I comma j is 0, and robot has special ability to neutralize robbers in at most 2 cells on its path, preventing them from stealing coins in those cells. Let's just, and we have to basically return maximum profit gained by robot on the route. So on the route means from 0 0 to m minus 1 n minus 1, bottom right corner. Now in this grid, what we are what is the ideal solution? Ideal solution is to neutralize. We can neutralize at most two robbers. So we can neutralize this one, this robber. So if we neutralize this, this would come out to be 0, because after neutralizing, the coins of I comma j becomes 0. And we can also neutralize this one. This is not required, but let's say we neutralize this. Now we have to find maximum profit of all the paths. Now what is maximum profit here? From 0 we go right, then go down, then go right, and then go down. Now gain over here is 0 plus 0, 1 plus 0 plus 3 plus 4, and answer here is 8. So that's why here answer is 8. Similarly, we are given another example where all the elements in the grid are 10. So we don't, here all of them are already positive. We don't need to use the second type of operation, the special ability to neutralize the robbers. And here maximum profit would be 40. And these are just normal constants. M cross n would be 25 into 10 raised to power 4. So of around 10 raised to power 5 of order. Now this condition at most two cells. If this was not there, then it would be a standard DP problem. Ij represents maximum gain till I comma j. So in this case, let's say we are at position I comma j. What two options we have? We either come from I minus j, I minus 1 comma j, or we either come from I comma j minus 1. So this is a down operation, coming down operation. This is coming up. Sorry, coming not up, coming towards right, and plus the coins at I comma j position here also. So these are the two transitions if there was no additional condition of at most two cells. Additional condition of this performing operation at most two times. So it is it would be obvious to add it as a state. So let's say we add it as a state. So what we have now is I j. This basically represents position, and let's call another variable op, which is number of operations performed till I and j. Now this will have multiple conditions. So let's say first two, let me just make them more. Let's say here we are coming down, here also we are coming down, here we are going towards right, and going towards right. So coming down means from I minus 1 we come to I. So I minus 1, j, I, j minus 1, and I, j minus 1. Now these are the first level of partition. Now another operation which separates all four operation is two-second type of operation. That means we use the we neutralize the robber. So let's just say if we do that operation, call it 1. If you don't do it, call it 0. Right and 0, right and 1. So now if we do that operation, we have to subtract operation -1 from previous state. And if we don't do that operation, there is then we have to take the coins which are present at I comma j position. Here also, if we do that operation, and if we don't do that if we do that neutralizing robber operation, we basically make a of I comma j equal to 0, and we don't need to add it again. So here, if we do that operation, it would be 0, and if we don't do it, we have to take it as it is. So these are the 4 transitions which are needed to be considered. So here I just wrote a tabular DP, not recursive. So I will give you idea about how it will look. So first of all, here there would be three states. So this is just I cross j DP. Now here there would be again 3 states: 0 operations, 1 operations, 2 operations. So if we do 0 operation, then it would be a of 0 comma 0, that number of coins. And if we do 1 operation and 2 operation, then it would be 0 comma 0. This would be a of 0. So this is the base condition. So on first cell, top left cell, if we do 0 operation, that means we have to take it. If we do 1 or 2 operations, then we don't have to take that. Then we can take 0 and 0. Now first of all, we will fill this row and this column, because it will be only dependent on its only one of the cells. So this will be only dependent on its previous, this will be only dependent on its upward. So when we are at this cell, so first we need to fill for 0, we need to fill for 1, we need to fill for 2. So for filling for 0, it would be its previous, that is dp of I minus 1 comma and j and 0 plus a of I j. For 1, we have two options. Either we fill from previous with one operation as it is, so don't increment the operation, or we can increment the operation j and take 2 as it is. Here it would be 1. Similarly, here also there are uh, two conditions, which two options: keep 2 as it is, and here it would be 0, and here it would be 1. Keep 2 as it is, but add a of ij. um, yeah, and if you, so this should be 1, this should be 0. So for 1, if we keep number of operations 1 itself, that means we are not doing any additional operation, so a of ij will be added. If we take transition from 0, that means there was operation performed at this position. So if it was performed, a of ij would become 0, and this would be so this would be 0. So for 2, there are two possibilities. If we don't increment the operation itself, so from previous column plus a of ij. we do not perform operation, so a of ij remains as it is. If we perform operation, we have to take 1 from previous, because total number of operations at this cell is 2. So if we performed it, then on previous cell there should be 1 number of operations, and hence we performed a of ij will become 0 and we don't need to add. So this will fill this row, this column. Now similarly we need to fill this based on, just make j minus 1 instead of I minus 1. Then we start iterating like this for then for each row, but from first index. Now here there would be two possibilities, I minus 1 also and j minus 1 also. So these same all conditions, uh, but two uh, for two possibilities, I minus 1 and j minus 1. So this is the whole solution. And finally, whatever answer is at this cell for 0, 1, 2, for all the possible operation, we take max of it and print max. So let me just show you the solution. First I tried with writing a recursive DP, but I then skipped it because generally I thought it will give TLE, so I skipped it. So let's just say see the solution. First of all, this nm declaration, then I have declared a variable which is limit, which is minus 10 raised power 15. Why I declared it? Because here if all the coins are negative, the answer could also be negative, that the maximum profit also can be negative. So if I have declared it 0, then while taking max in further transitions, it would give wrong answer. So I have declared limit minus 10 to the power 15 for initialization of DP state. So this is base condition 0 comma 0 position. So if we perform 0 operation, it is a of 0 0 itself, 1 and 2 operations, then uh, it will be 0. Then we fill the row, then we fill the first column, then first row, and then we fill all the other cells. You can do it based on this condition of if that element is negative. If it is positive, then we don't need to worry about performing operation. We can just take max from its previous state and add the current value. And for all the cells, we need to consider two possibilities, I minus 1 also and j minus 1. So down and right both operations. And finally, I'm iterating over 3. So dp of n minus 1, m minus 1, and 0, 1, 2, whatever operations we perform. So at this last cell, uh, all three possibilities, take max of it and return it as answer. Pretty standard DP problem, I would say. Let's move to third one. This is kind of annoying problem, I would say. Not annoying exactly, but I got unnecessary TLEs. I'm not sure why. I have basically same logic for both of this. In one I'm using BFS, in one I'm using DFS. But DFS1 gives me TLE and BFS1 gives me accepted. I'm not sure exactly why there is this issue, but let's see the solution first. So we are given two integers n and threshold, and also a vector which is 2D integer array ages, and ages contains a, b, and w. A and b are node numbers, so which represents there is a node from a to b with weight as w. Now this is a directed weighted graph. Now what we have to do is we have to remove some edges from it so that it satisfies the following conditions: that node 0 is reachable from all other nodes. The maximum edge weight in resulting graph is minimized, and each node at most have threshold outgoing edges. Now we need to return minimum possible maximum edge weight after removing the necessary edges, such that all the conditions are satisfied for that edge after removing all the necessary edges. So let's just take first example. This is one, this is one, this is one. Now in this graph, the answer is 1. So maximum edge weight is maximum edge weight which is possible 1. So we basically remove all the edges which have weights greater than 1. So which then graph would look like, so something like this. So this is 1, this is 1. Now here 0 is reachable from all the nodes. 2 can reach 0 by 2 1 0 path, 1 can reach 1 0, 3 has direct edge, and 4 can visit 0 via 3. So the first condition of this condition is satisfied, and the third condition, that is each node has at most threshold outgoing edges. The threshold here is 2, and each node outgoing edges are maximum 2. So 1 has 1, 2 has 1, 0 has 0, 3 has 1, 4 has 1. So none of them have greater than 2 outgoing edges. So condition is satisfied. Now if we keep maximum weight as 2, so if maximum weight, if we can minimum weight allowed, if we can uh, take it as 1, we can also take it as 2, we can also take it as 3, we can also take it as 6, 1 is 6, but we cannot take it as 0. So what it presents is a monotonic function. So for some x this is true, then for some x minus 1 it is false, and all the elements after x the conditions are satisfying. So we basically need to find that x. Let me give you one example. So in third example, the answer possible, the minimum weight for which all the conditions are satisfied. It's 2. So for 2, the condition is possible, that is true. So for 1, 0, it is false. For 3, 4 up to infinity, it is true. So this is nothing but a monotonic function. That means either it is increasing or it is either it is increasing or it is decreasing. So false, false, true, 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 or true, true, false, false, false. So you can consider it something like this: 0, 0, 1, 1, 1, or 1, 1, 1, 0, 0, 0. So in these types of functions, it is always best to use binary search. This is more a formal way of coming to the point that we have to use binary search. Also looking at this condition, we have to return minimum, or when question is about returning a minimum or maximum possible value, then most probably it is better to give a thought of using binary search. So I also did it. I didn't prove like this. I just thought we can use binary search, and then I implemented the solution. Now in binary search, let's say we fix mx. Mx is maximum weight allowed. That means we are basically removing all the edges which have weight greater than mx. So first condition, this is done. We are taking care of it using binary search. Now let's move to the condition where 0 is reachable from all nodes. Now this is a directed graph. So if one is able to reach 0, then we can say that if we reverse the whole graph, that means if we reverse all the edges, so something like this. So in original graph there was edge from 1 to 0. If we reverse all the edges, the graph would become there is an edge from 0 to 1. Then can we say that this interprets as all the nodes are reachable from 0? So if 0 is reachable from all the nodes, then in the reversed graph of it, all the nodes are reachable from 0. So here the starting was as any other node, but here there would be a single start, which is 0 itself. So this is a better way to check if uh, check this condition, that is 0 is reachable from all nodes. So what we do is, from original graph we reverse all the edges, and then we start traversal from 0 and check if all the nodes are visited. So this is how we can do it, and we also need to consider this weight. So only if, so while traversing the graph, if the weight is less than equal to mx, then only we will accept that edge and traverse, uh, let's call the child child node as v. Then only we will traverse that if the weight is less than equal to mx. If it is not, then we will not, that edge is removed, so we can traverse the child node. So this takes care of these two conditions. Now the third condition, from 2, let's say there are 5 uh, nodes, and one of them then goes to 0. These are, let's call it x, y, z, a, b. So x, y, z, a, b are 5 nodes, and let's say that threshold here is 2. Then we need to remove 3 edges basically. Now what here you need, what is important here is that from 0, if we want to reach, from 2, if we want to reach 0, there must be at least one path from which we can reach, the node 2 can reach 0. Here it would be 2b 0. So threshold, and in the example given, in the constraints given here, threshold will always be greater than equal to 1, and we only need to take care of that one path. So this condition can be neglected because we only need that one path, so we don't need to worry about this. We can remove these edges because we only require one path, and one, if there is any dependency from this node which goes to 0, then it would be taken care of that single path itself. We can remove this all the edges except the path which goes to 0. So whatever threshold we require for each node to reach 0, we only require one adjacent node or one edge. So this threshold is not used anywhere in the solution. So let me just go through the solution again. First of all, we write binary search on maximum weight allowed. Then when we fix the maximum weight, uh, to check if all the nodes are 0 is reachable from all the nodes, we reverse the graph and start traversing from 0 and check if all the nodes are possible, all the nodes are reachable from 0. And while traversing, only those edges are processed whose weight is less than equal to the mx which we have uh, calculated, which we have uh, processed in that binary search. So mx is basically made of low and high range in binary search. And for threshold, we can just ignore it. We don't need to worry about it. If there are multiple greater than threshold edges, we only need one edge. All other can be removed. So let's just see the solution first. First of all, I declared this answer high low values. Answer is -1 initially, 0 and 1 is 6. As maximum weight is 10 raised to 6. Then I declared an adjacency list of pairs. So what I'm doing is I'm storing weight in the adjacency list itself, but I have stored it in reverse order. So C of 1 to C of 0, there is an edge of weight C of 2. So edges of 1 to edges of 0, but with weight edges of 2, something like that. Then this is the condition where I'm checking if C of the target in any of edges, if it is not 0 itself, then our answer is -1, because 0 cannot be reached if 0 is not a target in any single edge. Then there is this binary search, while low less than equal to high, MD is the maximum weight allowed. Then I have declared a width vector, width of 0 would be 1. Then I'm running a BFS. Now, for BFS Q, then iterate over all its adjacents in adjacency list if they are not visited. So here there can be also cycles. So this condition is enough to ignore those. And also additionally, if the weight is less than equal to MD, then we push it. And finally, when BFS is complete, we check if any of the node is unvisited. If it is unvisited, we make CH equal to 0 and break. If CH is 1, that means all the nodes are visited. Update our answer, update the range, else also update the range, and finally return that answer. So this was third problem. So this solution gave me TLE where I was using DFS, and in DFS itself, for additionally checking the condition of cycles, there is this additional conditions, I would say. So this was giving me TLE, same solution, just instead of BFS I have DFS. Now here I used BFS. So this is commented and just BFS, and this got accepted. Ideally both of them should get accepted according to me, but that's fine. So my rank is 9977. Probably will get some minus in this contest. And fourth problem, only 83 solves. I will try to observe. I tried some logic, but it was not perfect, I would say. Yeah, so that's it from my side. Thank you for watching.